Here in this video I will explain you a very interesting result that you can find in a conditionally convergent series. So what do we mean by a conditionally convergent series? That is a series where this converges but not the absolute series. For example, this one, right? So this along with these negatives, it will converge by the alternating series test, but when you get the absolute value, it will be just the harmonic series which diverge. So these are called conditionally convergent series, right? Now let's take this one, right? We can prove that when you have this pattern, this plus and minus nature with this pattern, that's basically this series negative 1 to the power n plus 1, because it starts with the positive term and it starts at n equals 1 and goes up to infinity, right? And we can prove that it is equal to ln2, right? There is a certain method, and I am not going to explain you the method that we are going to prove this one. Okay, let's take it for granted. Okay, so now we know this one, right? Then let's multiply it by half, right? So we multiply each and every term by half. So the right hand side will be equal to this one and the left hand side will be equal to this one, right? Because now each and every term will be multiplied by half. Okay, so it will be like this, right? And then what we do is we insert zeros after each and every term. Okay, and then we add this one to the initial series, right? To this one, right? So we add the new series mentioned by 2 to the original series that we started to do the problem, right? So it will be this. Okay, and we are adding these two things together. So when you add the two series together, what you will get is something like this, right? If you just add the terms together, you will get this one. Now say for example 1 plus 0 will be equal to 1, and this 2 will get cancels out, and then 1 over 3 plus 0 will be 1 over 3, and negative 1 over 4 minus 1 over 4, negative 1 over 4, negative 1 over 4 will be negative 2 over 4, and that is equal to negative half, right? And then likewise you will get this series, but it's an interesting pattern because now this is the original series that we started, and here you can see that you will still have all these numbers arranged in a different order. See, they are arranged in a different order, but still you will get all these numbers, right? But when you look at the right hand side, since it is the addition of half ln2 along with this one, you will get 3 over 2 ln2. See, you have the same set of numbers but arranged differently, and you get 2 end result. This is a very kind of a mind-blowing result, okay? Because if it is the finite addition, let's say we are adding some finite numbers, okay, so the answer will be equal to, here in this case, 115, right? So no matter what rearrangement you use here, you will get the same number, okay? And that is true for any number of finite terms, but you can see that it is not the case when you have infinite addition, right? That's one of the main reasons that they have defined the infinite addition through the partial sums, because partial sums is the finite addition and we know how to deal with those. And here this is a different kind of a different world. When you are dealing with infinity, that's a totally different scenario, right? But now there are some things you should know. If the series is absolutely convergent, right, if the modulus is also converging, then whatever the rearrangement you have, you will get the same result. That's kind of a theorem that the mathematicians have proved, okay? And there's one more thing. There's a very famous mathematician called Riemann, okay? R-I-E-M-A-N-N, Riemann, and he proved that for any conditionally convergent series, right? What do we mean by conditionally converge? This will converge but not this, right? So for any conditionally convergent series and for any real number r, okay, we can have some sort of a rearrangement of these numbers and you can get the answer as r. So for any real number r, you can rearrange any conditionally convergent series and get the answer as r. Okay, so think about this for a moment. Like, you may not be able to figure out the proofs, right? But just think about these ideas. They are quite interesting, and like there are some nice results when it comes to the convergence, or rather the addition of infinite terms. So these are some examples which explains the importance of having these partial sums for the definition of an infinite addition. But anyway, all these things are true for the conditionally convergent series, okay? So just try to remember these results. You will not get any questions for the exam on these stuffs, but it's nice to have these ideas in mind, okay? For any real number, you can rearrange any given conditionally convergent series so that the answer of this series, that rearranged series, is equal to that given number. Say, like for example, if you take a real number like this, and we know that this is a conditionally convergent series, right? This person have proved that there is a certain rearrangement of this series, so that if you rearrange the terms according to that particular method, then the sum will be equal to this one, right? That's the basic idea of this statement made by Riemann, okay? Right, so with this one we will conclude the session for our week 7.